Article 450.27 of the National Electrical Code addresses safeguards for transformer installations that present a fire hazard. These safeguards apply regardless of the type of oil or insulating fluid used, including transformers filled with Envirotemp FR3 dielectric coolant. While Envirotemp FR3 is a fire-resistant fluid, it is not fireproof and it still poses a potential fire hazard due to its flammable nature. The safeguards outlined in 450.27 are essential to mitigate these hazards. The specific safeguards detailed in 450.27 cover several key areas. Firstly, location. Transformers should be located indoors in Class 1 hazardous classified locations or outdoors where readily accessible to fire personnel or protected by an automatic sprinkler system. Secondly, enclosure. Transformers should be enclosed in a vault or separate building. Thirdly, ventilation. Adequate ventilation must be provided to prevent the accumulation of combustible vapors. Fourthly, spill containment. A containment system should be in place to prevent the spreading of leaked fluid. Fifthly, fire extinguishing equipment. Suitable fire extinguishing equipment for Class B flammable liquid fire should be installed. The National Electrical Code Section 450.27 does not specify defined space separations for transformers with Envirotemp FR3 or other fire-resistant fluids. However, some guidelines are recommended to ensure safety. It is recommended to maintain a minimum distance of 10 feet from adjacent buildings to minimize the risk of fire spread. Openings in the roof where transformers are installed should be sealed to prevent fire spread from below. Consider installing fire walls to separate the transformer installation from adjacent areas. Other important considerations include verifying with the local authority if there are any additional requirements or restrictions for transformer installations, particularly on rooftops. Always follow the transformer manufacturer's specific instructions and recommendations for installation and operation. It is important to understand each of these topics. Firstly, the location of the transformer impacts the fire safety measures required. For indoor installations, especially in hazardous locations, more stringent requirements apply, such as the use of vaults or separate buildings to contain potential fires and explosions. Outdoor installations must be accessible to fire personnel so that they can quickly respond to any incidents, or an automatic sprinkler system is needed to suppress fires. Secondly, enclosures such as vaults or separate buildings provide a physical barrier to contain a fire and prevent it from spreading to other areas. These enclosures are typically constructed of fire-resistant materials such as concrete or masonry and are designed to withstand high temperatures and pressures. Thirdly, ventilation is crucial to prevent the buildup of flammable vapors inside the transformer enclosure. These vapors can be released from the insulating fluid during normal operation or in the event of a leak or spill. Proper ventilation helps to dissipate these vapors and reduce the risk of a fire or explosion. Fourthly, spill containment systems are designed to capture any insulating fluid that leaks from the transformer. This prevents the fluid from spreading to other areas where it could pose a fire hazard or contaminate the environment. Containment systems can include barriers, dikes, or collection tanks. Fifthly, having readily available fire extinguishing equipment, specifically designed for Class B fires involving flammable liquids, is essential for quickly suppressing a fire in a transformer installation. This equipment may include fire extinguishers, hose reels, or automatic fire suppression systems. The absence of specific space separation requirements in the NEC doesn't negate the need for careful planning and consideration of fire safety. The recommendation to maintain a minimum of 10 feet from adjacent buildings is a common practice to reduce the risk of fire spreading from the transformer to nearby structures. Sealing roof openings is important to prevent fire from spreading from the electrical room below to the roof area where the transformers are installed. This can be achieved by using fire-resistant materials to seal any gaps or cracks in the roof. Installing fire walls to separate the transformer installation from adjacent areas provides an additional layer of protection. Fire walls are designed to resist the spread of fire for a specified period, allowing time for evacuation and fire suppression. Local codes and regulations may have additional requirements or restrictions for transformer installations, especially on rooftops. It is essential to check with the local authority to ensure compliance with all applicable regulations. Transformer manufacturers' instructions provide valuable guidance on the proper installation, operation, and maintenance of the transformer. Following these instructions is essential for ensuring the safe and reliable operation of the equipment. Envirotemp FR3 fluid is a dielectric coolant made from edible seed oils and vegetable oils. It's designed as a more environmentally friendly and fire-resistant alternative to traditional mineral oil-based transformer oils. While FR3 is more fire-resistant than mineral oil, it is still combustible and can pose a fire hazard under certain conditions. Therefore, it's essential to implement the safeguards outlined in NEC Article 450.27 regardless of whether FR3 or another type of insulating fluid is used. The fire point of a fluid is the lowest temperature at which the vapors of that material will continue to burn for at least 5 seconds after ignition by an open flame. FR3 fluid has a significantly higher fire point than mineral oil, making it less likely to ignite and sustain a fire. Mineral oil typically has a fire point around 330 degrees Fahrenheit, while FR3's fire point is around 680 degrees Fahrenheit. The flash point, on the other hand, is the lowest temperature at which a liquid produces sufficient vapor to form an ignitable mixture with air near the surface of the liquid. Again, FR3 has a much higher flash point compared to mineral oil, further reducing the risk of ignition. Mineral oil's flash point is around 300 degrees Fahrenheit, whereas FR3's is around 610 degrees Fahrenheit. The auto-ignition temperature is the temperature at which a substance will spontaneously ignite in normal atmosphere without an external source of ignition, such as a flame or spark. FR3 also has a higher auto-ignition temperature than mineral oil, meaning it requires a higher temperature to spontaneously ignite. The higher fire point, flash point, and auto-ignition temperature of FR3 contribute to its enhanced fire resistance compared to mineral oil. However, it's crucial to remember that FR3 is not fireproof and it can still burn under certain conditions. Therefore, the safeguards in NEC 450.27 are still necessary. Transformer vaults are fire-resistant rooms designed to contain a transformer and any potential fire or explosion. Vaults are typically constructed of concrete or masonry and are designed to withstand high temperatures and pressures. The specific requirements for transformer vaults are outlined in NEC Article 450.41 through 450.48. These requirements cover aspects such as wall, roof, and floor construction, door and window specifications, ventilation, and drainage. The walls and roof of a transformer vault must have a fire resistance rating of at least 3 IOs according to NEC 450.42. This means they must be able to withstand exposure to fire for at least 3 IOs without structural failure. The floor of the vault must be able to withstand the weight of the transformer and any other equipment installed in the vault. Vaults must be provided with adequate ventilation to prevent the accumulation of flammable vapors. Ventilation can be achieved through natural means, such as vents or louvres, or through mechanical means, such as fans. The ventilation system must be designed to exhaust any flammable vapors to a safe location away from the building. Vaults must be designed to contain any spills or leaks of insulating fluid. This can be achieved through the use of a containment system, such as a dike or a collection tank. The containment system must be sized to hold the entire volume of insulating fluid in the transformer, plus an additional amount for rainfall or other sources of water. Doors and windows in a transformer vault must be fire-resistant and self-closing. Doors must have a fire-resistant rating of at least 3 IOs, and windows must be protected with fire-resistant shutters or glass. The purpose of these requirements is to prevent the spread of fire from the vault to other areas of the building. Transformer bushings are insulated devices that allow electrical conductors to pass through the transformer enclosure. Bushings are typically made of porcelain or epoxy and are designed to withstand high voltages and currents. Bushing failures can be a significant cause of transformer fires and explosions. Over time, bushings can deteriorate due to factors such as thermal cycling, moisture, and contamination. Deterioration can lead to insulation breakdown and eventual failure. Regular inspection and maintenance of transformer bushings are essential to prevent failures. Inspection should include visual examination for cracks, chips, or other signs of damage. Bushings should also be tested periodically to assess their insulation strength. There are several types of tests that can be performed on bushings, including insulation resistance tests, power factor tests, and capacitance tests. The results of these tests can be used to identify bushings that are at risk of failure. If a bushing is found to be damaged or defective, it should be replaced immediately. Replacing bushings can be a complex and time-consuming process, but it is essential to ensure the safe and reliable operation of the transformer. Regularly inspecting and maintaining your transformers is crucial to ensure its longevity and safety, and also to prevent fire accidents. Transformer protection devices are designed to protect the transformer from damage due to overloads, short circuits, and other abnormal conditions. These devices include fuses, circuit breakers, and protective relays. Fuses are overcurrent protection devices that melt and interrupt the circuit when the current exceeds a certain level. Fuses are simple and inexpensive, but they must be replaced after they have operated. Circuit breakers are overcurrent protection devices that automatically interrupt the circuit when the current exceeds a certain level. Circuit breakers can be reset after they have operated, making them more convenient than fuses. Protective relays are sophisticated electronic devices that monitor the transformer's operating conditions and initiate protective actions when abnormal conditions are detected. Protective relays can be programmed to trip circuit breakers, sound alarms, or perform other functions. The selection and coordination of transformer protection devices are critical to ensure that the transformer is adequately protected. Protection devices must be sized to protect the transformer from damage due to overloads and short circuits, but they must also be coordinated to prevent nuisance tripping. Nuisance tripping occurs when a protection device operates unnecessarily, interrupting power to the load. Coordinating protection devices involves selecting devices with appropriate characteristics and settings to ensure that they operate in the correct sequence and at the correct time. For example, if a fault occurs on the secondary side of a transformer, the secondary protection device should operate before the primary protection device. This prevents the fault from propagating upstream and causing damage to other equipment. Proper coordination of protection devices requires careful planning and analysis. Electrical engineers use software tools to model the electrical system and simulate fault conditions. These simulations help to determine the appropriate size and settings for protection devices. Regular testing and maintenance of transformer protection devices are essential to ensure that they operate correctly when needed. Protection devices should be tested periodically to verify that they are functioning properly and that their settings are still appropriate. Testing can involve injecting simulated fault currents into the protection devices and verifying that they operate as expected. In addition to overcurrent protection, transformers may also be equipped with other protective devices such as overvoltage protection, undervoltage protection, and differential protection. Overvoltage protection protects the transformer from damage due to excessive voltage. Undervoltage protection protects the transformer from damage due to low voltage. Differential protection protects the transformer from internal faults, such as winding faults or insulation failures. Fire suppression systems are designed to automatically detect and extinguish fires in transformer installations. These systems typically use a combination of detectors, control panels, and extinguishing agents. Detectors are used to sense the presence of fire. There are several types of fire detectors, including heat detectors, smoke detectors, and flame detectors. Heat detectors respond to changes in temperature. Smoke detectors respond to the presence of smoke particles. Flame detectors respond to the presence of flames. Control panels are used to monitor the detectors and activate the extinguishing system when a fire is detected. The control panel typically includes a power supply, a microprocessor, and a communications interface. Extinguishing agents are used to suppress the fire. There are several types of extinguishing agents, including water, foam, carbon dioxide, and dry chemical. Water is a common extinguishing agent that is effective for cooling and smothering fires. Foam is a mixture of water and a foaming agent that creates a blanket of foam over the fire, suppressing it by excluding oxygen. Carbon dioxide is a non-conductive gas that extinguishes fire by displacing oxygen. Dry chemical is a powder that extinguishes fire by interrupting the chemical chain reaction of combustion. The selection of the appropriate fire suppression system depends on the specific characteristics of the transformer installation and the type of fire hazard. Fire suppression systems can be designed to protect individual transformers or entire transformer substations. Some fire suppression systems are designed to automatically discharge extinguishing agents when a fire is detected. Other systems are designed to be manually activated by personnel. Regular inspection and maintenance of fire suppression systems are essential to ensure that they operate correctly when needed. Fire suppression systems should be inspected periodically to verify that all components are in good working order. The extinguishing agent should be tested to ensure that it is still effective. Fire drills should be conducted periodically to train personnel on how to respond to a fire emergency. Proper grounding of transformers is essential for safety and to prevent damage to equipment. Grounding provides a lower impedance path for fault currents to flow back to the source, allowing protective devices to quickly clear the fault. There are two main types of grounding systems used for transformers: solid grounding and impedance grounding. Solid grounding involves connecting the neutral point of the transformer directly to ground. This provides a very low impedance path for fault currents, resulting in fast fault clearing times. However, solid grounding can also result in high fault currents, which can cause damage to equipment and disrupt power system stability. Impedance grounding involves connecting the neutral point of the transformer to ground through an impedance, such as a resistor or a reactor. This limits the fault current, reducing the risk of damage to equipment and improving power system stability. However, impedance grounding also results in slower fault clearing times than solid grounding. The selection of the appropriate grounding system depends on the specific characteristics of the power system and the transformer installation. Factors to consider include the size of the transformer, the voltage level of the system, and the available fault current. Grounding conductors must be sized appropriately to carry the maximum fault current that is expected to flow through them. Grounding conductors must also be properly installed and connected to ensure a reliable grounding path. Regular inspection and testing of grounding systems are essential to ensure that they are functioning properly. Grounding conductors should be inspected periodically for corrosion and damage. Ground resistance measurements should be taken to verify that the grounding system is providing a low impedance path to ground. All of the topics discussed, from the fire point of FR3 fluids to grounding systems, are interconnected.